Most developers are still stuck in the naive RAG phase, retrieving a few chunks, stuffing them into a prompt, and praying for accuracy. In production, hope is not a strategy. Today, we are architecting an agentic research loop. We are building a system that doesn't just search, but reasons, critiques, and verifies its own data sources using OpenAI's O1 Preview and LangGraph. We are doing this because naive RAG is fundamentally broken for complex queries. When you rely on a single similarity search, you are at the mercy of your embedding model's top K results. If those results contain semantic noise or irrelevant context, your LLM will faithfully hallucinate based on that garbage. Furthermore, vector stores are static snapshots. They can't tell you if the information is stale. We need a verification loop that treats the first retrieval as a hypothesis and not a final answer. We need a system that can say, this context isn't good enough, and then goes back to find better data. The first point of failure in any RAG system is the user's query. Users are imprecise. If we take a raw, vague prompt and head straight to the vector database, we miss the mark 50% of the time. In an agentic workflow, we implement query decomposition. We use the LLM to break a complex intent into 3 to 5 distinct subqueries. This allows us to traverse the vector space from multiple angles, covering technical specs, latency benchmarks, and architectural constraints simultaneously. We aren't just looking for a keyword match anymore. We're mapping the entire problem space before we even attempt to answer. To manage this complexity, we need more than just a chat model. We are using OpenAI O1 Preview as our central reasoning engine. We are doing this because of its native chain of thought capabilities. While models like GPT-4o are excellent at pattern matching, O1 is designed for system-to thinking. It spends more time thinking before it acts, which is critical for planning a multi-step research strategy. It can anticipate logical gaps in the retrieved data and decide when it needs to switch from searching local documentation to hitting the live web API. The critique is our structural defense against hallucinations. After retrieval, the data enters a grading node. This is a fast, specialized step where we use a smaller model like GPT-4o Mini to perform a binary relevance check. Does this document actually contain the facts needed to answer the query? If the score is low, the critique rejects the context and triggers a new search. This gate ensures that the final synthesis engine only ever sees verified, high-quality data. By separating retrieval from evaluation, we eliminate the bias of the LLM simply trying to be helpful with bad information. Building this loop requires a shift in how we handle code. Standard LangChain expression language chains are directed acyclic graphs. They only move forward. But research is cyclic. We use LangGraph to maintain a persistent agent state. This state object acts as our shared memory, tracking the history of search queries, retrieved documents, and verification scores. LangGraph allows us to define edges that can loop back to previous nodes. If our critique says the data is insufficient, the graph routes the flow back to the planner. This persistence ensures that the agent doesn't repeat its mistakes. It knows what it already searched and why it failed. This is our master blueprint. We start with the planner to define the strategy. We move to the retrieval phase, pulling from both ChromaDB and the web. Then we hit the critique node. If the data is verified, we move to the final synthesis. If not, the state is updated and we loop back to the planner for a more refined search. This architecture is self-correcting, verifiable, and production ready. Let's get hands-on. We start by creating a new Python virtual environment and we activate it. Now that we have our Python virtual environment ready, we can install a few dependencies. We are installing the core LangChain ecosystem, LangGraph for our stateful orchestration, and Tavily Python for our live web intelligence. We also include ChromaDB as our vector store and python.env for loading environment variables from your .env file. When the dependencies have been installed, we create a new file called .env. Here we specify our OpenAI API key and our Tavily API key. And I just realized we made a small mistake. Instead of installing LangChain Tavily, we installed Python Tavily. Let's fix that now. Now that we have all dependencies set up, we need to create our main.py file. Now let's import some stuff. We're importing operator and annotated to handle state reduction. This is how we ensure our agent's memory grows rather than overwrites. We also import ChatOpenAI class for our O1 preview planner and our 4o mini grader. We use state graph from LangGraph to define the architecture and Tavily search to provide our agent with a window to the live web. In LangGraph, the state is our shared memory. We define agent state using a typed dict. Notice that the messages key uses the operator .at. This tells the graph to append new insights to the history instead of wiping the old messages. This is critical for cyclic loops. Without this, the agent forgets why its last search failed. We also include isVerified. This is our structural gate to control the research loop's exit. Now we're going to define our functional nodes. We start with the research planner. The research planner uses O1 module to turn a vague query into a search strategy. Next, we define the web researcher, which executes that strategy using Tavily. And finally, we define the critique node. Here the LLM audits the findings. If the data is insufficient, we flip the isVerified flag to false, forcing the system back into the research phase. This is how we eliminate hallucinations at the architectural level. Next, we're going to wire it all together. Here we define our state graph. We add our 3 nodes, and here we add our edges. From the start we move to the planner, from the planner we move to the researcher, and from the researcher we move to the critique. Now pay close attention to the add conditional edges. Here we have 2 paths. From the critique, you can go either to the planner if the research wasn't verified by our critique node, or if it was verified, we can move to the end. We also compile that graph and execute .stream on it. Inside the for loop, we print our outputs. I just realized there is one improvement that we should do. Here, when we tell the planner to create a search plan, we need to add this constraint. Always keep it under 400 characters long. This is needed because Tavily API requires your search queries to be under 400 characters. There is one more bug that we need to fix. This result here is a dictionary. We need to read the results out of this dictionary and iterate through them. We also replaced O1 preview with O1 because O1 preview is no longer existing. And we also changed the human message here to compare O1 with GPT-4o. Now let's see it in action. Let's open the terminal and type python main.py. The execution now is done. It can take a while, but it's worth it. Here you can see the step that it has taken. It first went through the planning stage, then it went to the execution phase, then to the verifying one, planning, then execution, verifying again, and on the second time that it tried to verify the new search, it succeeded. You now have the blueprint for using O1 preview as a reasoning brain and LangGraph as the nervous system for your agents. Remember, the key to production-grade AI isn't the size of your vector store. The key is your verification logic. If you enjoyed this video, please subscribe and leave a like.